In the lectures that we've had so far, we've talked about relative maximums and minimums and extremum. Um, Now we're going to talk about absolutes, which I've also kind of mentioned in those lectures in class by this time. But just to kind of reiterate some of this stuff, relative maximums are basically turning points where I go from increasing to decreasing, and relative minimums are places where I go from decreasing to increasing. Um, they oftentimes will be lowest points or highest points in a function, but not always guaranteed to be the highest point or the lowest point. Um, when I start talking about graphs that have or functions for a defined range of values, then I am talking about absolute maximums and minimums as being the highest point on the graph for that domain and the lowest point on the graph for that domain. So they show you some examples here, some absolute extreme values. Here we have an absolute min and max, which are also for that small region. Looks like they would also be the relative minimum and maximum that you would find using the first derivative. The second one's a quadratic, and if the domain's going on forever and ever, your x values go on forever and ever, that would have a minimum but no maximum, because the two ends keep going up forever and ever, and this does bottom out. We do have an absolute maximum value in the third one. It's also a situation where we would have a circumstance that's not differentiable. And as we talked about before, relative minimums and maximums can occur when f prime of x is not defined too. And what you see in the last picture is what a lot of cubic functions look like, where I really have no minimum or no maximum, at least no absolute minimums or maximums. So I may have some relative minimums and maximums, but no absolutes. So for absolute extreme values, if I have a continuous function on a closed interval from a to b, it's going to have both an absolute maximum value and an absolute minimum value, because I'm more or less saying that we're not going on forever and ever. We're going to stop at certain places. We want to find all critical numbers between a and b, and we also want to include a and b itself, the endpoints. Because oftentimes that's where, if there's going to be anything that's higher than a relative maximum or lower than a relative minimum, it's going to be as we approach those endpoints. So here, find the absolute extreme values of f of x, being x cubed minus 9x squared plus 15x, on the interval from 0 to 3. It is a polynomial function, so it is continuous, and the interval is closed, so extreme values will exist. If I had a rational function, I could still potentially have vertical asymptotes, and therefore I may not necessarily have that kind of situation, because it would go, around the asymptote, it might go up forever and or down forever at certain places. So because this is a continuous function, I could expect both of these to occur. So I do find the first derivative, which is 3x squared minus 18x plus 15. And I work on finding the zeros. So this would factor into 3 times x minus 1 times x minus 5, which means x equals 1 and x equals 5 are zeros, but 5 does not fall into the interval. So we eliminate it, okay? So sometimes you're given a domain that will encompass both critical points that you find, but sometimes you have to kind of look and say, okay, well, this one isn't going to be included in my domain. So now we're going to evaluate the original function using the remaining critical numbers and the endpoints. So x equals 1, it's the largest function value. Endpoints at 0 and 3, I have 0 and negative 9. Negative 9 is the smallest function value. So the largest, 7, and the smallest, negative 9, of the resulting values of the function are the absolute extreme values of f. So we have a maximum value of f is 7, which is occurring at x equals 1. And we have a minimum value of f, which is negative 9, occurring at x equals 3. So now here we have a graph of the region in front of us. The whole idea for me being able to do these is to be able to, kind of know what the graph looks like without actually having the graph in front of me, or if need be necessary, to create the graph from the given information I've gathered. I was able to answer the questions about the absolute maximum and the absolute minimum without the graph. And the graph that's being shown here is showing concavity that, I really should use the second derivative test to determine more specifically. But, but that's the whole purpose behind all of this work, is being able to more or less know what the graph is going to look like beforehand, because that's even useful if you're using a computer or a calculator, so that you know how to set your window to see what the graph should look like, just to verify to make sure that you're correct. So now it's your turn. I'm going to have you determine the absolute maximum and minimum values for a function, and then we'll go over the problem. So for this one here, you were asked to find the coordinates of the absolute maximum and minimum for the function below on the given interval of x without using the graphing feature of your calculator. And oftentimes, I know that typically the way I ask questions on quizzes and tests, and the way that those who write questions for like the finals and stuff for the math department, they usually will ask for the ordered pair coordinates, so the x and y value. So you get, and you need to find them anyway in order to determine which one is the highest point and lowest point. So, so for this one here, we want to find the absolute maximum and minimum. It is a rational function, but as you can see really quickly, there is no domain restriction because there is no value of x that you could substitute into the denominator to make it 0. So this would be a continuous function because it doesn't have a domain restriction. And we do have a finite domain being given, so this thing is going to reach a highest point and a lowest point. Now we're just asking to find where they are. So the first thing I do is I do the first derivative. A lot of the functions that you'll be given in the textbook, as long as you don't see a lot of multiplication and stuff going on in them to begin with, you'll generally be able to answer them a lot more easily if you, use the quotient property for the first time around, and then if you have to do the second derivative, which you really don't for this one, although you're going to see me make use of it to kind of show what the graph looks like, kind of going beyond what this problem wanted. You may want to simplify it a bit more before you have to go and take a second derivative. But that's what f prime of x is when I apply the quotient rule for derivatives. And with a little bit of simplifying, I get that f prime of x equals 1 minus x squared over x squared plus 1 quantity squared. Now I'm going to set this equal to 0 to find critical points. And really, for this to be equal to 0, 1 minus x squared has to be 0, which means x squared would equal 1, which means x itself could be plus or minus 1. So these are my potential critical values, and I'm going to use the first derivative test to determine what they are. Although I could go right to the second derivative test to determine what they are for sure. So I set my number line, and I just plug in some numbers that are on either side of these values into f prime to see what I get. And as I can see there, at -2 f prime, -2 and 2 f prime of x becomes -0.12, and at 0 f prime becomes 1. So I can see here that this function looks like it's going to be decreasing until I hit the x value of -1, increasing between -1 and 1, and then decreasing afterwards, which means that at -1 I'm going to have a relative or local minimum, and at x equals 1 I'm going to have a relative or local maximum. So I make note of that. I also make note of the endpoints at this point. So I take the endpoints and plug those in. And what I can see here is that, okay, well, clearly the lowest point I reach for these values of x occurs at -1, -0.5. and the highest point I reach occurs at 1, 0.5. So the two relative minimums and maximums I find using critical points are also the absolute minimum and absolute maximum, which is what the scope of this question was actually asking us to do and find. I'm going to go a little further with this, is to kind of go and see what the graph looks like. Because remember, the reason why we're doing things like this is to kind of be able to show what the graph looks like in the long run. So we have this information. If I go to the second derivative, I still use the quotient rule here because it's not much better to try using the quotient rule or using the product rule by making the denominator a -2 power instead isn't going to create any less work for me. So I tend to stick it out as it is. And plus, oftentimes the one good point about using the quotient rule at times is that what you end up with is a lot better able to be simplified, because you already have basically everything going on in the numerator with having the common denominator on the bottom. So when I'm able to simplify this, I get the function -2x times 3 minus x squared all over x squared plus 1. Setting that equal to 0 would give me x equals 0 and x equals plus or minus the square root of 3 as being possible inflection points. And when I run the second derivative test, I can see each one of them has a change in concavity about it. So to run this out in order to produce a plausible graph for this, we already had found the endpoints beforehand, the absolute minimum and maximum. And because of that and the information we had gathered to find where these were, we knew that f of x was increasing between the x values of -1 to 1, and it was decreasing between -5 to -1 and 1 to 5. For the information we gathered on the previous screen, f of x is concave up on the interval from -√3 to 0, as well as square root of 3 to 5. It's concave down on the interval from x values -5 to -√3, as well as from 0 to √3, which means the inflection points were at the x values -√3, 0, and √3. And I found the y values for each one of these by, again, plugging them back into the original function. So the inflection points are occurring at -√3, -0.4330 at 0, 0, and at √3, 0.4330. And so as a result, the graph looks somewhat like this. And so that is what this function looks like. I mean, yeah, I took this further than needed, but I just wanted to kind of make sure you knew how to go about making sure you found the rest of it, because sometimes they will ask you to produce graphs from it. But the final answer, the absolute maximum is at 1.5, and the absolute minimum is at -1, -0.5. If you have any questions, please feel free to ask about it. Have a good day. In the previous example, I had mentioned the second derivative test for absolute extreme values. And the second derivative test is a way to determine whether a function had a maximum or minimum at a particular critical number, and amounts simply to checking the sign of the second derivative. Basically, it's checking for the concavity. I mean, generally, if it is concave up and you're, well, at the critical point, you're going to have a minimum. If it's concave down, well, at the critical point, it means you have a maximum. And that's what it's basically you're checking there. So you're going to see it kind of referenced in this example as we go through it. So for applications of optimization, I mean, optimization is simply a type of problem where you're asked to determine like a maximum or a minimum of something. You know, you want to minimize costs, or you want to maximize the area you enclose, or any number of things they may ask you to do. In this case here, if a timber forest is allowed to grow for T years, the value of the timber increases in proportion to the square root of T, while maintenance costs are proportional to T. So therefore, after the forest, after T years, is of the form, the value of the forest is A times the square root of T minus B times T, where A and B are constant values. So taking a more specific example of this, the value of a timber forest after T years is given by the function V of T equaling 96 times the square root of T minus 6T in thousands of dollars for values of T greater than 0. They want to know when the value of the forest is going to be maximized, when it's going to be at its peak value. So we turn this function into exponential form because we really don't have a clearly defined rule for a square root. So we're just going to treat a square root of t as t to the 1/2. And I'm going to take a derivative of this. And when I take a derivative of the value of t, I get 48t to the negative 1/2 power minus 6 set equal to 0. And I want to set that equal to 0 because I'm looking for a critical point. So I would get 48t to the negative 1/2 power equaling 6. T to the negative 1/2 power would equal 6 over 48, which is 1/8. So we now reach a point that 1 over the square root of t equals 1 over 8, which means that the square root of t equals 8, which means t itself is 64. So we know that based off of the first derivative test, we do have a critical value at the t value of 64, which represents 64 years. So since there's only a single critical number and t equals 0, which makes the derivative undefined, is not in a domain, we can use the second derivative test. So when you get multiple values within a domain, then that gets to be a little bit problematic. But so we did a second derivative. So differentiating the derivative function 48t to the negative 1/2 power minus 6, we would get negative 24t to the negative 3/2 power, which is the same thing as having negative 24 over the square root of t cubed. This PowerPoint slide does not go over it. However, what the exact number that would be calculated is, but as they make a statement here, if you plug 64 in for t and then cube it and then square root it, you're going to end up, with basically what 8 cubed is, and that is a positive number. 24 is technically a positive number right now, but there is a negative sign in front of the fraction. So whatever I would plug in for t that could actually be square rooted, which means anything that's 0 or more at this point, that it's going to produce a negative value. And since that means it's concave down, I would be expecting to have a maximum at 64 here. So based off of that, I know that this is a maximum that's going to occur here. So when I now calculate that to finalize the answer, the value of the forest is going to be maximized after 64 years. And the value of the forest is going to be resulting from me plugging in that 64 into the original function. And I calculate 384, which stands for $384,000. They do show a little graph of what it would kind of look like, and that's a pretty accurate graph if you were to graph it, based on, not having many things shown there as far as like, how it's been, how the axes have been set up. But, it's good enough kind of sketch of it. But again, it wasn't needed because we're able to find these things using algebra and calculus and not have to have the graph in front of us. So let's have you give it a try on this following problem. Every calculus course, including business calculus, will often, you won't be able to escape it without doing what's called, affectionately as the box problem, where essentially you're given a sheet. In this case, it's a square sheet, but sometimes I've seen it where it's been rectangular. And, you're asked to take that square sheet and make a box, an open top box, that was had the maximum possible volume for that box. So here we have a square sheet that's 12 inches by 12 inches, and we're going to cut squares out of the corners and then fold it up to make this open top box. We want to find the volume of the largest box that can be made in this way. So they show you how the box is made, but so let's take this information and try to see if we can come up with, well, for us to maximize this, we have to come up with a volume formula. So here's a couple of factoids here. We start with a 12 inch by 12 inch square sheet. When we remove these sides, because I don't know how much I need to remove from these corners. I mean, that's part of the thing here is I'm trying to figure out, how I would cut this sheet to maximize the volume by forming this type of box. But I'm going to cut off x by x corners, square corners of an unknown length from each corner, and then fold them up. So basically, as a result of that, my length and width are both going to be 12 minus 2x to kind of represent the 12 inches it was originally minus 2 times the amounts I'm going to take off of both ends. And of course, the height of the box is going to be x. The reason why I make sure to define these things is because the volume of a box is found by doing length times width times height. And so I make up an expression there, and as you see there, I multiply it all out to come up with a formula for the volume of this box. And I do a derivative of that to get 12x squared minus 96x plus 144, and I do set it equal to 0. And I get x squared minus 8x plus 12, which factors into x minus 2 and x minus 6, which equals 0, which means x equals 2 or x equals 6 are possibilities. Now, before I go much further with this, and I do show a shine chart there, and I mean, there's a couple of things about x equaling 6 that I'm not going to want to look at. First of all, as I can see, if I just do a regular sine chart for it, I can see that if 6 were allowed, then I would have basically a minimum volume at that point. Okay? As a matter of fact, it's going to be an unrealistic volume because basically for me to be able to cut these square corners off of the sheet of metal to form the box, I can only go so far. I only have so much length to do that. I can't make the square boxes I call it the side, like 14 inches by 14 inches. I only have 12 inches to work with. So I have to keep in mind that based off of the information that we have, that my domain has to be values that go from 0 at the lower end, which if I don't cut off anything, I won't be able to make the box anyway, up to 6, which means that I would cut away the entire side, which basically means that, I'm going to have issues that I'm just basically making a smaller square sheet and not still able to fold it up into a box. So I only have one value, 2, where it reaches a maximum value and it's actually in the domain of possible x values. I could have also run the second derivative test at this point and I would show that it's actually concave down at 2. But I already took care of that by using the number line. So you can either run the the second derivative test to determine if it's truly a maximum or a minimum, or you can still use the number line method of doing it. It doesn't matter which one you use. They both have they're both accurate. So, but the important part is, I know if I cut off 2 inch by 2 inch squares from the corners, that I'm going to get the box with the largest volume. And since they're asking me to find what that volume is, I'm going to go back to the volume function I computed before, plug 2 back into it, and I get that the maximum volume is 128 cubic inches. So there is that example. As I said, you wouldn't be able to get out of a calculus course without doing the box problem. You're going to see another one in the next example where we optimize area. But I'm going to talk about something dealing with that because optimizing area is generally something that you can handle without necessarily using calculus, although you could also use calculus to do it. So that's the end of this one. If you have any questions, be sure to ask me in class. Another problem that is often used for students to practice some calculus techniques are actually like the quote-unquote fence against a river or fence against a barn or fence against a house type problem, where basically you're asked to enclose, in this case we're trying to make 2 rectangular enclosures that basically share a side with the river and share a common length between the 2 pens or enclosures. As I said, there's different variations of that. You might just have a single enclosure. You might have 3 enclosures. There's different versions of this problem out there, but they're all basically done in a very similar way. And I'm actually going to show a couple of methods for this. One's more calculus-oriented, and the other one is less so. So we have a farmer who wants to make 2 identical rectangular enclosures along a straight river, as in the diagram below. if he has 600 yards of fence, which basically means he has the materials to build 600 yards of fence, and if he sides along the river where there's no fence, because assuming that whatever he's closing in there is not going to go into the river to swim, it's just going to use it to drink, I guess. What should be the dimensions of each enclosure if the total area is to be maximized? So ultimately, we're looking to see like what the dimensions of a single enclosure is, so that the grand total area is maximized. So now, one of the first things is that you should take a picture that's presented in a textbook, or maybe get with all the nice graphics, and make it a little bit more workable. So I'm making it much more basic here. The blue bar is the river. This is an overhead view, and those brown areas, those brown lines represent the fence. And I'm going to introduce some variables in here. I'm going to call each one of these vertical slats the width of the enclosure, even though I'm not exactly sure if the width, because usually we let the width be the smaller of the two. If it's like rectangular, it's going to be like length is longer than width. But I'm just calling that W, and I'm calling the other ones X. And the reason why I'm doing that is some students will use X and Y, and then when they start thinking about a graph of this function, and they're graphing it on an XY axis, they don't realize is that what they're actually going to be graphing is an area function, and they let y be the area as well, and that causes confusion because you're letting y be both a dimension of these enclosures, and then you're letting it be the area, and then students will often use one for the other and vice versa, and that creates a whole bunch of issues with coming up with the correct solution, which is why I chose to use W instead of Y. Basically here, we need to come up, since we have two unknown values, I mean, we don't know either dimension of these pens. So I need to come up with two equations that relates them together. One of them is going to come from the amount of fence I use. Well, the first one going to come up is the area. So the area, the total area that I'm looking to maximize is going to be 2 times X times W. I wouldn't even be able to graph that. There's too many variables. Even if I let A be Y and I let X stay X, well, what's W going to be? Well, I can't let that be anything. I would need to be able to turn W into an expression in terms of X, but I would need a second equation to do that. And that second equation is going to come from the fence being used. Because I can see from the figure, I have 2 X's and 3 W's making up the fence. And that should total 600 yards. So, and what I'm going to do is I'm going to solve this for W. So W is going to equal 200 minus 2/3 X. And then what I can do with that is, now that I know what W equals, I can now rewrite the area function in terms of X only. I can actually make it a full-fledged function. So I get that the area function is 2x times the quantity 200 minus 2/3 X, which I can rewrite as negative 4/3 X squared plus 400X. So I now have a formula that represents the area, the total area of these enclosures combined. Now here's where I'm going to branch. Here's where I can branch off between two different solution methods, because either of them would have required you to get this far. Okay, one of them, the first one I'm going to show, I'm using calculus. So I'm going to take that first derivative, and I get negative 8/3 X plus 400 equaling 0, and I solve for X. And I get that X equals 150. Now, I should definitely go through and do other tests for this. I have to be aware of the domain value of X. Like for instance here, since the width is going to be 200 minus 2/3 X, X would have to be less than 300, because that at 300 the width would become nothing. You wouldn't really have an enclosure anymore. And again, X being 300 would take up the entire 600 yards of fencing just for those two parts of X. So, and W itself, I mean, the biggest it could be is 200, taking up all 3 spots for itself. So, because of that, I mean, it only reaches one value between those, the values of x that you could possibly have. I could use a second derivative test, and the second derivative test would be basically that a double prime is negative 8/3 for any value of x, and if it's negative 8/3 for any value of x, it's going to be negative 8/3 for an x value of 150, which means it's concave down at 150, which would indicate it does have a maximum there. I don't show all that because it's just not enough space. So, but it does reach a maximum when x equals 150. And since we're looking for the dimensions, it's not asking me to find what the area is, although I could calculate it. The width is going to be the result of me taking this formula right here, at top here, and essentially, plugging the x value in. It's going to give me the other value. So looks like I labeled width as being, according to our standard, because it was smaller than what x was. X would be good lengths. So each pen would have dimensions 100 yards by 150 yards, and that would maximize the area. So that's the way we could use calculus to do that. The fact of the matter is, I didn't really need to use calculus for this, and usually a lot of circumstances where area, especially for a rectangular enclosure, or enclosures is being used, I often am not going to need it because I'm going to end up with a quadratic function. And we should already know enough about quadratic functions based off of what we've already studied about them. I know that at this point I have a quadratic function for the area, and in that quadratic function I have a leading coefficient that's negative 4/3. So I know I have a quadratic function, which means it's a parabola. The negative 4/3 is telling me, since I have a negative leading coefficient, it's going to open downward, which means it is reaching a maximum. That maximum will occur at its vertex. And the vertex is found on the axis of symmetry. And the axis of symmetry is found by using this formula here, x equals negative b over 2a. So, again, negative 4/3 being the value for A, 400 being the value of B. So I plug those numbers in, and as you can see, I do get the x equaling 150 again. And from here on out, it's basically, where we went to with the other one. I find W by plugging that in, still get the 100, and I still make the determination that the enclosure is going to be 100 yards by 150 yards if I want to maximize the total area. So we had methods that actually came from algebra that let us take care of this. But this method that we come from algebra actually comes from calculus. It was just a shortcut that was often allowed us to study algebra a little bit more successfully. And that's a lot of times what mathematics is used to do. It's to make certain things easier. But anyway, let me tell you what I'm talking about here. A typical quadratic function, which a lot of area functions are going to be, is going to be f of x equaling ax squared plus bx plus c. And we know it's quadratic, and we know it's going to have, a vertex, which either will be a minimum point or a maximum point. So it's going to be a critical point of some sort. And I would normally calculate the critical point by taking the derivative. So if I take the derivative of f of x in this very general case, f prime of x would be 2ax plus b, which of course I would set equal to 0 when I'm looking for the critical point, in this case the vertex. So for me to do that, set that equal to 0 and solve for x, I would subtract b from both sides and then divide both sides by 2a. So that formula is just the exact result of what I would get from doing the first derivative of a quadratic function. It's just that we had this method, and you learned this method before you actually studied the stuff that made this method. So, but that's why with optimizing a lot of area problems, you could either use the calculus, which in essence you're kind of doing if you use this formula, because it was developed with calculus, or you could just use this formula and use the techniques that you learned about in algebra. And that's going to be the same thing for the example you're going to do next, even though you're going to be dealing with a situation where pi is involved. But have a look at this, and we'll go over it. So for your turn here, you were asked to find, you have a running track that has semicircular ends, which means half circles, and you want the perimeter to be exactly 440 yards. I want you to find the dimensions of X and R that would maximize the area of the rectangle itself. So we're only maximizing this part in here. I could do the problem where I'm maximizing the total area, but that would involve a slightly more difficult function to work with, and that's why they're probably only telling you to maximize the rectangle part. Now, they do tell us about the perimeter. When they mean by the perimeter is including the circular part. So all this around here is the perimeter. Right here. So you can see here we have two semicircular parts and we have two straightaway parts which are labeled as X. So these two circles combined, these two half circles make up one circle. So having the perimeter of the circle, which is also known as the circumference, 2 pi r, is no big surprise we have that. And of course, two x's along with that would make up the total perimeter of this track. So now we want to maximize the area of this field. And as you can see, we have this perimeter that should total 440 yards. And I solve for x in order to get this x in terms of r. Because I'm now going to notice that 2r is basically the other side of the rectangle. We know one side is x, we know the other one is 2r. And because of that, the area of the rectangle is going to be 2r times x. That formula as it is not going to be useful to me because of the fact that, I have too many variables. So I'm going to turn this area function and make it in terms of r only. So I'm going to have a of r equaling 2r times 220 minus pi r, which is what I found x to be. And of course, now at this point, I distribute it out, and I get that a of r equals negative 2 pi r squared plus 440 r. So even if, no matter which method I use here, I can still use quadratic information. And the fact that, this is still a quadratic function. I do have an irrational number as the leading coefficient, but I also do know it is negative. Which means that this function, in terms of r, if I had an r-axis and an a-axis, it's going to open downward and be a parabola, and it's going to have a maximum at the vertex. I just have to find out where that vertex is. So I can either use negative b over 2a, which is a formula that resulted from calculus, as I showed in the previous slide, or I can just do the derivative and set it equal to 0. So if I do that, I get negative 4 pi r plus 440 equals 0, which means 4 pi r would be 440, which means r would be 110 over pi. And then I could calculate x by going back to the formula I have for x, replacing r with 110 over pi. And if I do that, I get 110. So basically, the dimensions x and r that would maximize the area of that rectangular portion of the field would be when x is 110 feet, or when r is 110 over pi, or approximately 35 feet. And that's the end of that problem. If you have any questions, please be sure to ask about it. Have a good day. Now for example 4 here, I am skipping right to 3.5, and the reason being is that 3.4 basically has just a lot of other circumstances involving areas and volumes, or circumstances where they've already given you a formula and they're asking you to find maximums and minimums. So there's really nothing new in section 3.4 because it's really just a section that goes over more optimization problems and just different varieties of them. So there's really nothing new as far as content goes in 3.4. In 3.5, there's two circumstances that they cover, which deals with things that aren't relatively apparent and that need to have some background on in order to do them. One of them deals with inventory costs, which is basically determining like certain sizes that you should produce and based off of storage and things like that. So in order to minimize your costs overall. And another one's going to be dealing with what they call maximum sustainable yield. So those are the two examples that I'm going to be going over. This first one's going to deal, of course, with the minimizing of inventory costs. So in business, you're going to have storage costs. If you are, whether you're selling something and you need to reorder it and get it back in stock, and then the cost, of course, to actually do the reordering. But you need a place to put it, so you need to have costs to store it, and you may have to store it under certain conditions and things like that, and have space for that. Or if you're producing things and you need to have a warehouse before it gets shipped out, you also have storage costs and production costs, which which basically comes in the same categories of what your order costs would be. So, they give an example here. A furniture store expects to sell 250 sofas in a year. It could order 250 all at once. However, you'd have to have space to find all 250 of those sofas, and that could cause a lot of maximizing of costs, for the storage costs. If you order many small lots, then 50 orders each throughout the year, you're going to have high reorder costs. Or if you're doing a lot of if you're producing these and do like 50 runs of 5 sofas each, usually the setup and making of them has some specific costs along with how many you order. So that's going to maximize your reorder / production costs, because you have those fixed setup costs every time you're doing it. So basically, the best order size or lot size is going to be one that minimizes the total cost, one that has the best combination of these two costs together that makes it as small as possible. So the example here is a furniture showroom expects to sell 250 sofas in a year. Each sofa costs the store $300, and there is a fixed charge of $500 per order. So basically, to place an order to replenish your stock for your showroom, you're going to have to pay $500 plus, whatever the cost per sofa is. And so, like here, I'd have $300 for each sofa plus $500 just for other shipping and handling or whatever you may want to call it. To store each sofa, if I break it down per sofa, it costs $100 to store a sofa for a year. So we want to figure out how large should each order be and how often should orders be placed to minimize inventory costs. Now, of course, the inventory cost would be the total cost of what I reorder as well as what I store. So we're going to let X be this lot size that we're looking to find out about it. Of course, 250 divided by that lot size is going to be the number of orders that are placed in that given year. So once I find the lot size, I can calculate how many reorders I'm going to be doing. As far as storage cost goes, if the sofas sell steadily through the year, and if the store reorders X more whenever the stock runs out, so basically, we're trying to figure out this lot size. We're saying, okay, the store's going to reorder this many each time it does a reorder. Then in general, the average inventory is going to be X over 2. Basically halfway, between, the highest amount of your inventory and having nothing at all when you have to reorder. So the average inventory size is X over 2. It's important to kind of know that because that's going to kind of get me to know what the storage cost for that inventory is going to be on average. The inventory level rises from the lot size X down to 0 with an average inventory of X over 2 sofas throughout the year. So that's why it's the average inventory. So because it costs $100 to store a sofa for a year, The total annual storage costs are the storage cost per item plus the average number of items. So in this case here, it's going to be $100 times x over 2, which is basically 50x. I don't know if they simplify it here yet. Yeah, 50x. So those are that represents my storage costs. I also have the reorder cost. The cost per order is going to be $300 times x, that's lot size, how many I'm ordering, plus $500 in fixed charges. So that's my cost per order. I'm going to have X number of orders of that. Okay. Or no, 250 over X number of orders. That's right. Yeah. X is the lot size. 250 divided by X is going to be the number of orders, which I still don't know yet. I still want to figure that out. So in order to figure out, the reorder costs, it's going to be the cost per order times the number of orders. So it's going to be 300X plus 500 times 250 over X. And of course now, the total cost, the total inventory cost is going to be the storage costs added with the reorder costs. So here they have 100 times x over 2, which I don't know why I just didn't rewrite it as 50x again, plus 300x plus 500 times 250x. And if I simplify this a little bit, I get 50x plus 75,000 plus 125,000 x to the negative 1. Now we're making that x to the negative 1 because obviously I'm looking to minimize this total cost, so I'm going to be using a derivative to see where that minimum is going to be. So if I minimize this, by differentiating it, I get this function 50 minus 125,000 x to the negative 2 power, which is the same thing as having 50 minus 125,000 over x squared. Setting that equal to 0, I would get 50x squared equaling 125,000 by doing a couple steps. Divide both sides by 50, you get 2,500, and then square rooting both sides. X would equal 50. I should also try to verify that this is going to produce a minimum. So when I do the second derivative, which is going to be 250,000 times x to the negative 3, or the same thing as 250,000 over x cubed, if I plug 50 into that, well, it's going to be it might be a smaller number, but 250,000 divided by 50 cubed is going to be a positive number. And since the second derivative is positive at that point, 50, I'm expecting it to be concave down, which means, or concave up, sorry. I'm just having trouble with that day. Concave up, which means I am going to have a minimum. So since we know the lot size is 50, we're going to have 50 sofas for each order. And since there's 250 sofas yearly, I'm going to have 5 orders throughout the year. And that's how we do the inventory cost. Now, this could be applied to production costs with the storage involved, which they're going to have you make use of. Just anything where there's any kind of inventory cost, whether it's production or for selling purposes, you're going to use this kind of setup to do it. For whether it's lot sizes or production runs, they're kind of the same thing. So let's have you try your hand at it and see what you can produce for the following question. So this question here, very similar to inventory costs, because an inventory cost is like how much you're keeping for the purpose of you selling, whereas a production run is basically very similar, except you're the producer, as you're keeping track of like how many you're going to need to have on hand to send out to various suppliers. So here, a toy manufacturer estimates the demand for a doll to be 10,000 dolls per year. Each doll costs $5 to manufacture, plus setup costs of $800 for each production run. Now again, setup costs could be things like having the electricity in the plant, the workers, various other things, so creating molds, whatever it might be. There's just fixed costs that go along with it. Each doll costs $4 to store for a year. How many should be manufactured at a time, and how many production runs should there be to minimize costs? So as I said, this is basically the same thing as when I was doing inventory costs or doing lot sizes for reorders. Production runs are just like when I do a reorder lot size and stuff, that's incoming, whereas production runs means outgoing. So it really does. It's really the same principle, just from a different viewpoint. So, X is going to be the number of dolls manufactured in a single production run. Now, that production run, a production run is like, how many are being produced in a set period of time that's been defined. And production runs can, occur over, a long period of time too. Throughout the year. So it isn't like it's like, well, I'm going to work for this many days and then the rest of the days off. No, it just means like the production run, before you would slow down and then, maybe get other tasks completed and things like that. And then before you run another run of it. So X over 2 is going to be the average inventory, or the average, what's the average amount we're going to have on hand to send out to the various stores or whatever the case may be. So the manufacturer cost is going to be the cost per run times the number of production runs. Well, it costs $5 to manufacture a single doll, so 5 times X plus $100. That's going to be the cost for each run. The number of runs I'm going to have to do is going to be 10,000 divided by the number of dolls produced in each run. So this function here gives me the manufacturing cost for the dolls. The storage cost is going to be the average inventory, which is always going to be X over 2. And that's the case that they're having you do, because we're always assuming a steady decline. These dolls are going to be moving out of the warehouse at a fairly constant rate, whereas it may have situations where it might go up and down as far as how fast they're moving out. So that requires much more sophisticated math, and we're not ready for that yet. So here we're just kind of assuming it's a steady moving from the warehouse out into the stores. So our average inventory is going to be X over 2. The storage cost per doll is $4. So I'm going to have for the total storage cost to be X over 2 times 4. Then, of course, the total costs, the total production cost or total manufacturer cost is going to be given to me by adding the two together. And so the cost function for this is going to be 50,000 plus 8 million over X plus 2X. That's the function for the total cost. With that function now, I can start looking for a minimum for that cost. So I take in the function I came up with in the previous set of steps. I'm going to let this be 2x plus 8 million x to the negative 1 power plus 50,000, because that's going to make it a little easier to do the derivative rule. The quotient rule won't make it any easier for that middle term. And I end up getting that the derivative is 2 minus 8 million x to the negative 2, which is 2 minus 8 million over x squared. I'm going to set that equal to 0 and solve for x. And I get that x would equal 2,000. So based off of this, we have a critical value when the lot size is chosen to be 2,000. I do want to make sure that this is going to minimize the cost. So I should run either like do a number line or run the second derivative test. We can't have a lot size that's 0 or under, because that means we're not making anything. A lot size could go up to 10,000. Because that's something I figured I had to produce in a given year. That'd be a one long run though. I do the second derivative, and I get that second derivative ends up becomes 16 million over x cubed. No matter what positive number I plug in for x, this is going to be positive. I showed it what the actual value is, it's positive. But the fact that the second derivative is producing a positive result at 2000 means it is concave up there, and being concave up means I am reaching a minimum. So I know I'm reaching a minimum cost when my lot size or my number being produced in a run is 2000. And the minimum cost will be $58,000 for that. Now, it's not asking me for what that minimum cost is. I just happen to calculate it. It's asking me two questions. How many should be manufactured at a time? And how many production runs should there be to minimize the costs? So to answer that question now, to minimize costs, each production run should manufacture 2,000 dolls, which would mean that the toy manufacturer should have 5 production runs per year. That's the end of this example. If you have any further questions, please feel free to ask about them. Have a good day. The other application of optimization that we're studying deals with the maximum sustainable yield, which is basically industry like fishing and any other kind of thing that deals with maybe livestock or any animal population that's going to be quote unquote harvested for food purposes. Is something that we often use for doing optimization. If you harvest some of the population, it means there's more food for other resources in the remaining population, so it will expand and replace the harvested portion. If you take too large of a harvest of animals, you're going to kill off the animal population. If you don't take enough, then you get situations like we sometimes have here in Pennsylvania when we have like the deer population basically starving to death because there's too many of them out there, which is why they oftentimes will cull them. So what we do is give it a function that represents the population growth for the reproduction function for a given animal population. We like to determine what the population size would be best to keep it at in order for anything that's harvested will be replaced within the next year, and not to take too many or too few and cause problems. So we want to find that maximum sustainable yield that can be harvested year after year and still have the population return to its previous level the following year. So for some animals, we get one can determine a reproduction function called f of p, and this is going to be something that's often given to you, so you don't have to worry about coming up with it yourself. How they come up with it is something we're not getting into, at least not at this moment. So, but it gives the expected population a year from now if the present population is p. So, so suppose we have a reproduction function f and a current population of a size p. And what they're showing here is that the amount of growth will be basically, this function being used for that population minus the population that's currently there. That's going to represent the growth. So the difference between what I'm going to produce in a year from now with that population and what the current population is. So f of p minus p is the growth function for a population. That's what we call the yield function. The yield is going to be essentially how many can be taken away from the population and still have it maintain essentially that same level in its population. So that's what they call the sustainable yield, and that's what the function y of p is. It's equal to the growth function for population minus the population for that year. Now this is showing why they often will just set the function f prime of p equal to 1 in order to come up with the maximum sustainable yield. I mean, basically, you're going to be maximizing y prime of p, but they kind of show how that directly translates into f prime of p equaling 1. I don't really approach it that way because it seems like this is extra facts they're trying to get you to memorize for it where it's not needed. Um, so, and what I often need to do is make sure that I am reaching a maximum, so a second derivative test usually comes in handy for that. So the maximum sustainable yield occurs when the growth for the population function or the reproduction function, so derivative equals 1. And the maximum sustainable yield is then y of p equals f of p minus p for the whatever p value makes the first derivative equal to 1. Once we count the calculation, the population that gives us the maximum sustainable yield, we can then actually calculate the maximum yield. So for example, the reproduction function for the American lobster is in an East Coast fishing area is f of p equals negative 0.02 p squared plus 2p. Where both of these f of p and p are in thousands. So whatever answer I would get here would be thousands of lobsters. We want to find the population that gives the maximum sustainable yield, and we want to find the size of that yield. So, which basically means, like, if we keep it like at a certain size, and we could take this many of it, and then, okay, whatever's left is going to replenish the rest of them. So they're showing here that I differentiate f prime of p and set it equal to 1. You could just do, y of p minus p, f of p minus p for the y of p and do y prime of p and set equal to 0. You get the same thing. And essentially, you get p to equal 25. Now, y double prime of p and f double prime of p are equal to the same thing because the minus 1 that would appear and 1 would disappear when you do the second derivative. So, so since the f double prime of p equals negative 0.04, that would indicate that we are concave down at p being 25, or any value of p for that matter, which means we are reaching a maximum there. So we do know that 25,000 is the population size that we would like to keep the lobsters at. The yield is going to be f of p minus p. So when I do that, I calculate this. I plug in 25. And when I plug that in, I would get, I'm just double checking their math because I found some errors with this already that I had to exclude out of here. I get 12.5, which stands for 12,500. So the population size for the maximum sustainable yield is 25,000, and the yield is 12,500 lobsters. So with this in mind, I want you to give the next one a try. So for the question you were asked to do, you were given the reproduction function of the Canadian snowshoe hare, which is f of p equals negative 0.025 p squared plus 4p, where p and f of p are in thousands. You were asked to find the population that gives the maximum sustainable yield and the size of the yield. Now, you have to remember that these reproduction functions, represent, like, how fast they're growing under certain conditions, and they also account for overpopulation too. And the thing about the like hares or rabbits or any other kind of rodent population, they grow pretty quickly and in great numbers. So they can overpopulate really quickly. So this one actually produces a circumstance that's a little bit different, and you'll probably see it in a lot of these other functions. And that's whenever we have a population size that's going to produce a yield that's bigger than the population size. And that's because they grow so rapidly that, I could take out a large number of these hare and still have just as many to take the next year, and as long as I maintain the population at a certain size. So now I'm working a little bit differently. I don't focus my attention on f so much as I do the y function. I know that the yield function y of p is given to me by f of p minus p. I know that y prime of p is equal to f prime of p minus 1, which would be a natural consequence of me taking a derivative. And of course, because of that, y double prime p and f double prime p are going to be the same function by that point, because the only thing that's different between y prime of p and f prime of p is a minus 1, which when I differentiate that becomes nothing. So the yield function is going to be negative 0.025 p squared plus 4p minus p, which ends up being negative 0.025 p squared plus 3p. When I differentiate that, I get negative 0.05 p plus 3, which I in turn set equal to 0 to find out the population size that's going to produce that to happen. And I get a p-value of 60. Now, just to double check that, when I do the second derivative, I end up with negative 0.05, which means any p-value is going to produce negative 0.05. So here at 60, or anywhere else for that matter, it's going to have a negative value, which means it's concave down, which does mean that I do expect this to produce a maximum at 60. Now, here's the deal, So the population size I need to make sure that the snowshoe hare is kept at is 60,000. If I do that, because they do multiply so rapidly, when I plug that into the yield function, and I'm showing that we do have that, so when I plug it into the yield function, I actually end up with 90. So if I make it a point to keep the snowshoe hare population to 60,000 this year, I'm going to have 90,000 I could take next year, and then when I yield that, I'm going to be able to say, oh, well, I'll keep it at 60,000 by taking 90,000 away. So here's an instance where I have a yield that's more than the population size. It's kind of a weird circumstance, but again, it's because this particular population grows so rapidly, and rabbits and rodents and things like that do often have overpopulation problems as a result, because the sustainable yield of them is often going to be much higher than the population that you would need to keep it at to keep that yield. So that's all there is for this example. If you have any further questions, please be sure to ask. Have a good day.